Hello and welcome to another video. In this video we're going to be working on Furthest building you can reach. And it's a pretty interesting problem compared to the ones before. It's definitely a little bit harder than those. So in this one you have an inch-array heights representing the heights of buildings, some bricks and some ladders. You start your journey from building 0, you move to the next building by possibly using bricks or ladders. While moving from building I to I+1, if the current building's height is greater than or equal to the next building's height, you do not need to use ladders or bricks. And otherwise you need to use the height difference bricks. Or a ladder, either one. Your ladders can be whatever, doesn't matter the height difference, you can just use one ladder. Return the furthest building you can reach if you use the given ladders or bricks. So in this first example, this is decreasing, so this costs us nothing. Here we have an increasing part, so we can either use 5 bricks or a ladder. Either one is fine in this problem. Here is decreasing again, so this costs us 0, so we can write 0, 0, and then these are the two locations where you can use bricks or ladders, the lines. And it doesn't really matter which way you do it, because no matter what you pick, you're not going to be able to make this jump here, which costs you 5, because you only have one ladder. So the farthest you can get to is this location over here, and they describe how to do that. So you want to return 4, because that's the index of the building. And the second example is the one we're going to go through in detail. And the third example, you have no ladders, but you can just use only bricks. So this costs you 0 because it's decreasing. This costs you 16. And this costs you 0 because it's decreasing again. So you need 16 bricks total to make the whole thing. And so the first thing I thought of, and I think it's pretty intuitive if you've done a lot of LeetCode problems, is DP, right? You have 2 choices at every building. If it's decreasing, it costs you nothing, right? So you can just recurse to the next one. But if it's increasing, you can either pick brick or bricks or ladder, right? Try both of those, see which one gives you the best result. So for that solution, the problem with that solution is you need to keep track of index, brick count, so number of bricks, and number of ladders. And if we actually look at the constraints here, the bricks is 10 to the 9th, so keeping track of bricks is basically impossible. So we can't do anything that keeps tracks of bricks in a state. Like even if it was just only keeping track of bricks, this wouldn't work. So we have to try something else. And another intuitive idea that I'm going to go through is basically we have to know a few things. For one thing, if we know we can't reach this building, like any building, we know we can't reach anything after it, right? So if a building is not reachable, like if we can figure that out somehow, then we know that if we go in order, if we say okay, well, let's just start maybe, at this building, say, is it reachable? Is this reachable? Is this reachable? Is this reachable? And if one of these isn't, then we can just stop, right? So if this isn't reachable, we're done. We return this. Don't care about that, right? Because to get to one building, you need to go to the previous building. You can't jump or anything. That's one thing that's going to help us. Another thing is all we really need to know, if you think about it, is let's say we get to some building. Let's say we get to this building. Let's actually go through this. It's going to be cleaner. So here's that same example 2, written out in an array, just so we can work with it a little bit better. So let's say we're trying to get to this building over here. Well, if we knew how many total jumps, how many total increasing sequences we have. So here we have 10 bricks and 2 ladders. So let's write that down. So 10 bricks, 2 ladders. But if we're trying to get to this building, if we know how many increasing sequences we have and how many bricks it would cost for each one, then let's see what happens. So this is an increasing sequence. It costs us 8 bricks. This is decreasing, so it costs us nothing. Increasing costs us 5 bricks. Decreasing costs us nothing. And increasing costs us 15 bricks. Well, why don't we just try a greedy, not necessarily greedy, but we know we have 10 bricks. So in order to get here, if it's possible, why don't we just use as many bricks as possible to cover however many routes we can? In this case, we can only cover one of them, but which one would we rather use for bricks? Would we rather use this or this? 15 is too much. We'd rather use the 5, right? Because this is less bricks. So then maybe later on we have more bricks available. So here, to get here, you need 5 bricks, right? And you need a ladder here and a ladder here. Is that doable? Yeah, it is. And so that's kind of the idea, is we're basically going to keep track of wherever we're at, like how many bricks does it take to get here, and how many bricks can we actually use. And the way we're going to do that is, instead of keeping track of how many bricks does it take to get here, we're actually going to only keep track of like what's the most bricks we can use and where can we put them in the best way possible. And we're going to do that using a heap. So we're going to keep track of how many like brick sequences can we use, and then how many total jumps do we need. And so let's say we have like 3 brick sequences, or like three brick like paths we can make. And then we have like 5 total increasing moves. Then we know, like, okay, well, if we can make 3 and we need 5, then we know the other 2 need to be ladders. And do we have enough ladders? If we do, then we can get here. If not, we just return this index. So let's kind of walk through what this would look like with a heap. And we're going to use a max heap, because the idea is we want to store all of our brick paths. And then whenever we put in a new one, when we have to get rid of one, right? Like let's say this is 8, this is 5, this is 15. Let's say we're putting in like a new path, or even this 15, right? Like let's say we have all of these in our heap. Well, we're going to keep track of like the total sum of these bricks, right? So even going back here, like once we put in this 5, our total sum is 13. So ideally what we want to do is we want to get rid of the biggest path, and we want to store as many paths as possible that add up to the bricks that we have or less. Right? So if we can make everything using bricks, that's fine. If not, we're just going to keep getting rid of the biggest path and seeing like, do we have enough ladders to cover that? So let's kind of walk through how this is going to work using a max heap. Okay. So obviously you can get to the first building, so there's not much to do there. But so we check this building. And we're just going to compare our building to the one before. If this is not increasing, we can just continue, because like there's nothing, like to get here is free, doesn't matter. So in this case, it's not free. It costs us 8 bricks. Let's move this. Yeah, we can just put it down here with our heap. So this distance is 8, right? Like this is how many bricks it costs. And we're going to keep track of that in a variable. We can call that like use bricks or something. And I'll show you why this is going to be useful. So we have 8 bricks. We're also going to keep track of how many increasing paths we have, right? So we can call this like maybe moves or something. Or like increasing, or we can just call it increasing paths, I guess. So increasing paths, we have 1 so far, right? It's this path right here. This is the only increasing path so far. Now we're going to check, like once we have this in here, we're going to check, is our sum of our used bricks more than the bricks we have? And if it is, we have to get rid of bricks. Right now, we can just use our bricks and we're good. So if we're good, then we check, okay, so how many paths can we make with bricks, which is just the length of the heap, right? The length of the heap is 1. And how many paths do we need to make? So we need to make 1 path, and we already have 1 thing in the brick. So we know we're good. We don't even need to use any ladders. So we know this is reachable. So we can just like maybe check this off or something. So check that off. Then we go to the next one. This is decreasing. So this is free, right? Like we don't really need to do anything here. It's not an increasing path. This costs us 0. So this is fine. Then we go over here. This is increasing. So we have another increasing path. So increasing path is going to be 2. Oh, why can't I? There we go. And how many bricks does it cost us here for this path? It costs us 5. So we're going to put 5 into our max heap. I'm just not going to have this in order, but no, it's a max heap, so we'll get rid of the biggest element. And how many bricks did we use now? So we had whatever we had, and then we added 5. So our bricks is 13. Then once again, we check, did we use more bricks than we have? Yes, right? And we can even leave these like increasing paths to show this for later. So this is an increasing path, this is an increasing path. We can even draw it like this to make it a little bit cleaner. So increasing. Okay. So here, we don't have enough bricks for this. So like I said, which one, we can build one of these paths. Well, which one do we want to keep? We want to keep the 5, right? So we want to get rid of this 8 because that, like we want to build the shortest path we can with the bricks and use the rest for our ladders, right? It's like the greedy strategy. So now our used bricks is 5. And now it's pretty easy because we have we can store a cumulative total, and every time we pop from our heap, we can just decrement the total. And every time we push to the heap, we can increment the total, so we don't have to do like a sum or anything, right? You need this to be a log n operation. And so here, so we have 5 bricks used. We need 2 paths, and the length of our heap is 1. So we can make one path with bricks, and the other one we need to make a ladder. Do we have enough ladders? Yes, we do. We have 2 ladders, so this is reachable. Actually, I don't think I need to draw these check marks. Just know that like if we've been here already, it's reachable. Okay, so we go over here. So this is decreasing, so this is free. So we can just keep going. Okay, here we go. So this is increasing again. This costs us 15. Yeah, it costs us 15. So we're going to put 15 into the heap. We're going to check, and this is an increasing path again. So we're going to increment our increasing paths because those are the ones we care about. Decreasing are free. We don't really do anything. We check, is the size of our heap bigger than our bricks? So we also needed to update this variable. So now we have 20 bricks in our heap. This is bigger than 10. So we're going to pop. What do we want to pop? We want to pop the biggest one. So we're going to pop this. So now we're back to 5. And how many increasing paths do we have? We have 3. How many paths do we have with bricks? Just 1. So we need 2 ladders, which we have. So we can get here, right? Because we can use this bricks, and this could be ladder. So we keep going. Okay, this costs us 2 increasing, so we're going to add a 2 into our max heap. We're going to update these things, so increasing paths, now we have 4. Used bricks, we have 7. And we check, is this bigger than the bricks we have? No, it's not. Okay, so how many paths can we build with each? Well, the length of our heap is 2, so we can build 2 paths with bricks. That means we need 2 with ladders, right? Because we need 4 total. So do we have 2 ladders? Yes, we do. So we're good there. This is decreasing, so this is free. Then this is 16 bricks. Increasing again. So we're going to update our increasing paths. We're going to add 16 bricks. So this is 23. Add 16 bricks. This is too much again, right? So we will get rid of our biggest element. So we'll get rid of the 16. And since we got rid of it, now our bricks is back down to 7. So can we get here? Let's see. We need 5 paths. We have 2 paths with bricks. That means we need 3 ladders. We only have 2. So we can't get here. That means we just return the one before this because that's the one we could get to, right? And assuming we could get here, then this loop would be done. So then as a default, you can just return the last index in the array as the thing you can get to, right? Like if we were able to get here, that means we were able to get to every single index. So we would just return this index. So the answer here should be index 7 to return. And that is indeed what they have. So hopefully it's clear. You use these increasing paths to figure out like how many actual paths do I need to build with bricks and ladders. You want to be greedy using a heap to build the smallest paths with bricks that are possible. You want to use as many bricks as you can, and then just figure out like, can I use ladders for the rest? And hopefully it's also clear why you can't use DP, because just using bricks as a state would already be too big. Well, now our solution is basically n log n and relies on the heights length, which is fine. So we can code that. So we are going to have our heap of bricks. We can call it heap. Maybe you can use better variable names, but yeah. And then we can say bricks used equals 0, and our increasing paths equals 0. So now we need to loop through all our buildings. Remember, we can always get to the first building because you're not like, you start there. So we're going to start at every building other than the first building. So we'll start over here. So we can say for I in range 1 length heights, we're going to calculate the difference from this building to the one before. So difference equals heights I minus heights I minus 1. And we only care about positive differences. Actually, So yeah, we care about positive differences, right? Because like here, we would do 12 minus 4 would be positive difference. If it's a 0 difference or negative, that means it's not an increasing path, so we don't care. So we can say if difference is less than or equal to 0, just continue. This is like a free jump. We don't need to do anything. So if it's not, then we need to increment increasing paths. And we are going to push this current difference into our heap as like, we're going to say, okay, we'll try to build this with bricks. So we're going to heap push into the heap. And because we are using a max heap, so I didn't talk about this in the picture, but because we're using a max heap, we're just going to store all our numbers as negative. So because in Python, it's built using a min heap. In other language, you can actually just use a max heap. So we'll just store these as negative, and then when we pop, we'll pop the smallest number, which will be our biggest number, because that'll be negative. So we're going to push negative difference, which is the number of bricks we need in the negative number of bricks we need here to build this path. Then we are going to increment our bricks used, right? Literally just like this picture here. So use bricks, increment it once you push into the heap, plus equals difference. Then we need to basically say while our bricks used is greater than bricks. We don't have enough bricks to do this, so let's just keep popping from the heap. So we can say bricks used plus equals heap pop heap. And the reason this will work is it'll give you the most negative, or it'll give you either the smallest number. Actually, sorry, every number in the heap will be negative. So it will give you the most negative number, which is like the most bricks you can use. So this number is going to be negative. That's what we could add to it. Yeah. And bricks used is going to be positive. So you'll have some positive number plus some negative number of bricks used. So it's going to be subtracting. Then we just need to check if we can actually build. Like we need to figure out, okay, is our number of brick paths plus our number of ladders equal to or greater than increasing paths. So we can say if length of the heap plus ladders is less than increasing paths, then we don't have enough to do this, so we just return I minus 1. This wasn't reachable, so we'll just return the one before. Otherwise, if we were able to get to this, otherwise if we were able to get to the whole thing, through the whole thing, then we just return the last building in our height. So it's just going to be the length of heights minus 1. And let's see here. Yeah, pretty good. Okay, and so let's go through time and space pretty quickly. So time, so essentially, let's just think about it. So this is of n. A heap push is a log n operation, so that's going to be n log n. And so it's n log n based on the size of the heap. And worst case scenario, the heap will have every single element, right? Like let's say your bricks is like, I don't know, trillion or whatever, and you can just fit all of these increasing paths, and they are all increasing paths. Then the size of your heap would be n, so this would be n log n, where n is the length of the heights. Yeah, in this part, like you can only heap pop once for every heap push, so it'll be like 2 times n log n or something, worst case scenario, which is n log n time complexity. And the space, so we are using, this is a constant variable, but for the heap is not a constant variable. So this is going to be of n, because like I said, worst case, imagine all your buildings are increasing and you can fit them all into the heap. That would be order n, where n is length of the heights. But yeah, I think that's going to be all for this one. So definitely kind of an interesting problem. There are a lot of like editorial solutions that I read. There's like a binary search one. It seems a little bit unintuitive to me. I think this one I came up with relatively fast after checking that DP didn't work. So an important thing here is, like I said, make sure to look at the constraints. And if you don't know, so a really easy trick to remind you one more time is something like 10 to the 8th fails. So just if you're considering DP, think about, write down your dimensions and write down like what they would be. So in this case, it would be like bricks times, so it'd be like 10 to the 9 times 10 to the 5 times 10 to the 5 for ladders, which would be like obviously way too big. Yeah, and I would say if you've done a decent amount of LeetCode, the DP should kind of be your like brute force quote unquote solution, and then look for something better. Because if you can get DP to work, that's usually pretty good. But in this case, we can't, so we have to come up with something else. And yeah, that's going to be all for this one. If you did like this video, please like it, and please subscribe to the channel. And I'll see you in the next one. Thanks for watching.